Hello, we will now do chapter 9, section 2. This would be the first part. There's two parts. This is the main part. So this is part 1 of chapter 9, section 2. But it's the main part of it. The second video just deals with kind of some accessory sort of issues in regards to a one proportion z-test. But and that's the deal with this section, is being able to perform a one proportion z-test. So we're going to do two different ones. They have slightly different sort of tests, but they're both one proportion z-tests. So here we go. So this one says a worker at the health department of, it should be health, not Heath, the health department of a county in a southern state is researching health issues in her county. In particular, she wishes to know if the proportion, not the mean, the proportion, in her county that eat at least 5 servings of fruit and vegetables each day has changed in the past year after an outreach program had been instituted. A year ago, pardon me, 34% of the adults said that they ate at least 5 servings of fruits or vegetables a day. This year, she takes an SRS of 250 adults in her county and finds that 102 of them eat at least 5 servings of fruits and vegetables a day. Does it appear the outreach program has worked? Was it effective in increasing this proportion? Perform a test of significance, otherwise known as a hypothesis test. Whenever you have to perform a test of significance or a hypothesis test, you got to do 5 things, and it follows the THAME acronym. Remember, with an interval, it was the TAME acronym, but we've added on an H into that, hypotheses. So it's going to be the type of inference. We have to state the hypotheses. The assumptions are going to be the same as last chapter, effectively. Then we have the mechanics, which is certainly different from last chapter, and then the ending. Okay, so it's a very similar sort of thing. But the premise that is going on here is that, all right, so we have this claim or this old value of 34%. And so we took a sample, so our p hat, all right, and so that would be 102 out of 250. And so that is equal to 0.408. So that is our estimate in essence. How different is that? Okay. Is there, I mean, it's certainly more than 34%, but is it statistically significantly more? That's the question we're really answering. So the first thing we have to do when you have to do a test is, whenever you do an inference, you have to state the type of inference you're doing. This is what is known as a one proportion z-test. Okay, and that's going to be on your calculator if you forget, but please get the name right. And technically, if you wrote the formula down, which I'm going to show you, you get credit for that as well, but it's easier just to write that. The second thing, and this is new to this chapter, is hypotheses. It was mentioned in section 1. And so we need a null and an alternative hypothesis. So our null hypothesis is just going to be whatever's claimed is true, the status quo, or no change, no difference. He said a year ago, 34% said they ate at least 5 servings of fruits and vegetables, and now we're seeing if that's changed. So the status quo is that P is equal to 0.34. So in this section, your null hypothesis is always going to look like this, with P equal to some number. Do not put anything but equal to there. Not greater than, less than. It's got to be equal to. And P goes there, not P hat, please. The alternative is what you're testing for. So H sub A is what you're testing for, or what you think might be true. And in this case, you notice it says, does it appear the outreach program is effective in increasing this proportion? So we are seeing if it's increasing, if it's larger than now. And by the way, it's not ethical to look at the sample value and to put this as greater than. Say, well, the sample value is greater than, I'm going to go greater than. No, you have to have another reason in the problem to go greater than. And if you don't have a reason to go greater than or less than, put not equal to there, and it'll be a two-sided test. All right, so, and as we discussed last section, whenever you write your hypotheses and use a variable, you have to define that variable. P is the proportion of all adults in this county that eat 5 servings of fruits and veggies each day this year. That is what we're in essence estimating, okay? Because last year it was 34%. All right, so there you go. So there's the type of inference, there's your hypotheses. Now your assumptions are basically the same as last chapter. The A is for the assumptions, and we must verify them. So this is just like last chapter, in essence. There's a little bitty twist on it, but otherwise known as verifying the conditions. Very popular question in the world of AP Stats. Okay, very popular. Of course, the acronym is SIN. Please become good at sinning, please. It's going to be asked about, it's emphasized. So the SRS, is it an SRS or random? Well, you would look, it says SRS right there. So you'll say that. It says an SRS was taken. So say it with me now. Thus, random condition is met. I mean, you're going to be saying that every problem the rest of the year, basically, or some form of it. Then we have independence. Now, this aspect of the word independence is that our sample size can't be more than 10% of our population. And so what you're going to do for this independence, because the reason, once again, is because we're not using replacement when we're taking our sample. So when we take these 250 adults out of the population, all right, we are slightly changing it. But as long as the population is big enough, it's not going to change it significantly. How big does it need to be? At least 10 times your sample size. And so you would say, you will say this: there must be at least, and multiply the sample size times 10, 2,500 adults in this county for our little n to be less than or equal to 0.1 times our big N. Our sample size to be less than or equal to 0.1 times our population size, okay? Just like last chapter, okay? And then it's important to know the why, or the result of this. The result of this is that when you use your formula for standard error, it will work, okay? The formula for standard error will work. And then lastly is normality. Now this is where it's a little bit different. You know, normality in regards to proportions, N times P and N times 1 minus P are greater than or equal to 10. Now, last chapter we used P hat there, but this chapter we're using this value, what is known as P naught. P naught is the hypothesized value. You know, the whole reasoning of this hypothesis test is, if we assume the null is true, what's the probability we're going to get a sample value this unusual? And that probability is going to be p-value. But we do the whole thing sort of assuming the null is true. Okay. So, well, if we assume the null is true, the best measurement for this would be 0.34, the p naught. So we use the p naught in this chapter. Of course, we can't use p naught last chapter because we didn't have one. So we had to use the only thing we had, which was p hat. So anyway, so our sample size is 200. So this would be 250. So that's times 0.34. And that would be 250 times 0.66, which is 1 minus that. And so that ends up being 85. That ends up being 165. And they're greater than or equal to 10. Okay. You don't have to write down the letters there. I would show the multiplication just to clearly show that you're using the P naught. That would be good. Oh, it's very important to say, thus normality is met. Thus, normality is met. So there you go. So there's your conditions. Once again, very similar to last chapter, very important. You're sinning. There you go. Now, for your mechanics, for a test, the M is for mechanics. All right. Now, when we did a confidence interval, the mechanics was just the interval. When you do a hypothesis test, your mechanics, you got to write down two numbers. You got to write down your test statistic, and your p-value, those two numbers. Now, I'm going to show you how to use your calculator to get it, okay? You do have to understand how to use the formula, but I'm going to show you how you use your calculator. The test statistic in this chapter is the Z test statistic. And then we have the p-value. So this is how you use your calculator to get it. You can always use your calculator to get it, but like I said, you do need to understand how to use the formula, but let's just use our calculator. And so to do this, you're going to hit the stat button and you go to tests and you go down to option 5. So this chapter is all about option 5 and option 6. Okay. So option 5, one proportion z-test. And if you forget the name, there it is. There it is. There it is. And so, okay, great. So, so one proportion z-test. Boom, we hit enter. So our P naught is 0.34. P naught, 0.34, the hypothesized P. Our X, our number of successes, is 102. And in our sample size is 250. Okay. And then this line is our alternative. Our alternative could be not equal to, could be less than, or could be greater than. Okay. In this case, it was greater than. So I'll click on greater than, hit enter on greater than, then just hit calculate. And there it is. There's your test statistic p-value. So this would be 2.269695, let's say, plenty of sig figs. And then the p-value is 0.01161. So this would be 0.01161. So that's how you find those. And so that would be full credit for test statistic and p-value. Okay. The big number's p-value. Now, why we have a test statistic, a sort of tradition in stats that identifies which sort of test you're doing, and it is used to find the p-value if you didn't have a calculator, but you can always use your calculator. So there you go. And so that's that. And so the last part of your test is your ending, which it just the ending with this is to make a conclusion. Make a conclusion with the p-value. You're going to make a decision with your p-value. All right, and we talked about this the first section. If your p-value is below your alpha value, then you reject the null. So in this case, nowhere up here does it say use an alpha value of 0.05 or alpha value of 0.01 or anything like that, okay? So what we'll do is we use alpha of 0.05. Alpha value is just a value. If your p-value is below that value, you would reject the null. Now, like for this one, so let's say if we pick alpha as 0.05, which is what we'll do since they don't give us one. So what we will say is this. We will say this p-value, 0.01161, make sure and say what it is less than our alpha, 0.05, so I reject the null hypothesis, okay? The p-value is low, I reject the hope, all right? And then you would say, thus, I have convincing evidence that, and then you restate the alternative. The proportion of people who eat their veggies in this county is greater than 0.34. You state it in context, okay? That the proportion of all adults in this county that eat their fruits and veggies is greater than 0.34. So there is drawing a proper conclusion. You clearly have compared your p-value with your alpha value. Since it's less than 0.05, you reject the null and have convincing evidence for the alternative, and you say what the alternative is, okay? If the p-value is greater than 0.05, you would say, I failed to reject the null. I do not have convincing evidence that, and you restate the alternative in context. That's what you're going to do. Now, if, by the way, so let's just pretend the alpha had been 0.01. Let's just pretend it said up here, use a significance level of 0.01. Alpha significance level is 0.01. Well, our p-value would be greater than our alpha value. In that case, we would fail to reject the null, and we would fail to have convincing evidence that and restate the alternative, okay? So that's that, and that's how you do a hypothesis test. Now, all right, so let me show you how you do need to understand what I'm fixing to say as far as the mechanics, all right, as far as using the formula. So using the formula, I'm going to write this down here to find your test statistic p-value, okay? You can always do that, but you need to understand this because frequently in multiple choice questions, it'll ask you to use the formula. So what we'll do is we'll use the formula to find our test statistic. Well, let me grab a formula sheet. So to find our test stat using a formula, Z is equal to, okay, so on your formula sheet, standardized test statistic, and that's what Z is. It is the statistic minus the parameter over the standard error of the statistic. Now, our statistic here is P hat, okay? Our parameter is P. We don't know what P is, but once again, we are doing this whole test sort of assuming the null is true, so we use the P naught of 0.34. And then standard error of the statistic. Well, where are we going to find that formula? I think you know. On page 2, we've been doing this past couple of chapters, and so the standard error is that, and we use P naught, not P hat, okay? So we'll use P naught there, the square root of P times 1 minus P over N. So that formula would thus become, it would be our statistic 0.408 minus our hypothesized parameter 0.34 over the square root of, and we're using P naught here, so that's 0.34 times 0.66 over our sample size, which is 250. And when we do that, it is equal to about 2.2697, let's say. That's what that's equal to, okay? And so now, how do we find a p-value? Well, let's think about this. Now, this is going back to get our p-value, like what we did in chapter 7 using our sampling distribution. So the p-value is this: assuming the null is true and things are centered at 0.34, that is assuming that is our true value, our sampling distribution, all the possible values p hats could take will be centered at 0.34. So assuming 0.34 is right, what's the probability we're going to get our sample value, which is 0.408, or more unusual or larger? And the reason I'm going larger is because that's what it says there. Greater than. So I go greater than, and so we'll do normal CDF there. So let's do normal CDF. So we shall do second vars normal CDF from 0.408 to infinity. So 0.408 to infinity. All right, the mean is 0.34, and then the standard deviation is the square root of 0.34 times 0.66 divided by 250. That's just using the formula for standard error, right? And so we go like that, and boom, we got ourselves a p-value, see? So that's how you, kind of do it by hand. You can also use tables, and we're not going to really worry about that. The last thing, the last method, the third method of finding a p-value is to use your test statistic, which is sort of the traditional way of doing it. And so what we would do there is, this is a standardized value, and so we'll use the standard normal curve. So, and the standard normal curve is mean of 0, standard deviation of 1, like that. So our test statistic is way out here, 2.27, let's say, and then the alternative is greater than, so it's like that. And so we'll do normal CDF from 2.2697 to infinity, mean of 0, standard deviation of 1, the standard normal curve, and that would give us our p-value. So that would be the other way, okay? But like I said, you can use your calculator, but you do need to understand that. Okay, great. All right, so now let's look at this other problem. There's a couple little twists on this, but it's sort of the same thing. So let's see if you can figure this out. So a researcher wishes to test the hypothesis that 60% of the trees in a forest have a particular fungus. He takes a random sample of 320 of the trees and finds that 210 of them have the fungus. Perform a two-sided hypothesis test. Also create a 95% confidence interval and comment on how the p-value relates to the interval and its confidence level. So that would be another important thing that you've got to be able to do, make the connection between the interval and the p-value. So anyway, and this one's a two-sided test. And by the way, if it didn't say perform a two-sided test, you do it anyway, because in order to do a one-sided test, in other words, greater than or less than for your alternative, you'd have to have a reason to do that in the problem. It have to be stated. If it doesn't say, then you do two-sided. All right, so the first thing we're going to do is we are going to state the type of inference. We're going to do our THAME acronym, type of inference. And once again, this is a one proportion z-test. That's what it is. Then we state our hypotheses. Our null hypothesis is the status quo or whatever's claimed in the problem, and it would be 60%. P is equal to 0.6. Our alternative is what we suspect might be true, and of course it told us to do two-sided, which means goes not equal to in your alternative. And you have to define P. When you write P, you have to find it. So P is equal to the proportion of all the trees that have the fungus. There we go. The proportion of all the trees that have the fungus, okay? And so then we, of course, the next one would be our assumptions. We verify our assumptions, otherwise known as our conditions, and we sin, right? We sin. You would say, it says random sample. Random sample, it has to be SRS or random. So it says a random sample was taken, so random condition is met. So random condition is met. Great. Independence will be our next thing. In other words, is our population size at least 10 times our sample size? Okay, so you multiply that times 10. So you would say there must be at least 3,200 trees in this forest for our little n to be less than or equal to 0.1 times our big N, for our sample size to be less than or equal to 10% of our population size. And lastly, normality. So for normality, remember our n times our p naught and our n times 1 minus p naught must be greater than or equal to 10. So our n here is 320, and our p naught is 0.6, and that's 192. And then that's 320, and 1 minus, that's 0.4, and so that's 128. They're both greater than or equal to 10, so you'd say thus normality is met. So we've been doing that for a couple chapters now. Thus normality is met. There's your, that's maybe the most asked about part of the whole thing, okay? And so let's find our test statistic p-value. Now we'll just use the calculator. And so your mechanics, the A, we got the TH, and then the mechanics. The mechanics, always don't forget to write down your test statistic, please. That happens a lot. We need your test stat, and we need your p-value. Yes, we do. Test stat, p-value. So our test stat, so let's do this. And so we are going to go stat, we go tests, and we go down to 1 proportion z-test. Boom. And so we enter in our null hypothesis value is 0.6. So we go 0.6. Our X, our number of successes, 102 no, it's not. It's 210. It's 210, right? So we would say 210. And then our sample size is 320. And then our alternative is not equal to. So we're going 9. This is a 2-sided test, okay? So we are going calculate. And so there we go. There's our test stat p-value. So Z is equal to 2.054 approximately. And our p-value is 0.03998. Okay. So there's our test stat and p-value. Write p-value. Don't just write p, because p is kind of a different thing to us. So write p-value. And so then our ending. So I'm gonna come back and I'm gonna make this calculation by hand in a minute, because there's something I want to say about it. But you can just do it like this. And then remember our ending, we have to make a decision, draw a conclusion about our p-value. So we have to mention, what are we going to do with this p-value? If the p-value is low, you reject the hoe. Okay? And therefore that's what we're going to do, because this is below 0.05. This p-value, and you say what it is, 0.03998. It's less than 0.05. And I use that because they didn't give us an alpha up here. Okay? So we use 0.05. So I reject the null hypothesis. Okay? Thus, I have, what do we have? Convincing evidence. Convincing evidence that, and then you restate the alternative in context. The proportion of all the trees with the fungus is not equal to 0.6. That the proportion of all the trees with this fungus is not equal to 0.6. That's how you do a one proportion z-test, and that's the heart of the chapter, okay? That's the heart of the chapter. You know, please, what is emphasized, once again, please, yes, you got to kick butt with the assumptions. That's asked about more than anything. And then the second thing is you got to kick butt with this statement here. You got to be able to interpret a p-value. You got to be able to draw a conclusion with a p-value, rather. If the p-value is low, you reject the hoe. If the p-value was above, now let's just pretend, just for the fun of it, that they gave us up here, hey, alpha is equal to 0.01. Let's pretend that. Then you would say the p-value is greater than 0.01. So I fail to reject the null, and I do not have convincing evidence that and restate the alternative. Okay, so there you go. That's going to take a little bit of practice, but you can do it. Okay, and then before we address this final issue with the confidence interval, I want to show you how this was, how this p-value, how you calculate it by hand. Okay, so here is our, all right, so, and it's using a sampling distribution, just like with chapter 7. So the whole premise of this hypothesis test, if 0.6 is true, what's the probability we would get a sample value as unusual as 210 out of 3 over 320 just by chance? So our sampling distribution, so you need to really understand this, is centered at the hypothesized value. It's approximately normal as we determined above. Now our p hat, our sample value, so that's 210 out of 320. And that in fact is equal to, I believe, 0.65625. Okay. And so that is somewhere over here. Okay. Somewhere over here, 0.65625. And so we need this area. Okay. But we also need to understand that the p-value, because it's a two-sided test, we have to include an equal-sized tail over here that is less than, because it's not just the probability of this one or bigger, it's the probability of that unusual or more unusual. In other words, we have to include the second tail over here. So when we do normal CDF to find this p-value, we're going to have to multiply it by 2 in essence. So we'll do normal CDF. So let's do this. So we shall do, so we go second distribution, normal CDF from that number, 0.65625 to infinity, our mean is 0.6, and our standard error would be the square root of 0.6 times 0.4 divided by 320, like that. So there we go, boom. And so notice, looky there, is that right? So it's a two-sided test, you got to say times 2. So our p-value is equal to 0.01999 times 2, and that is equal to 0.03998. Okay, so that's what happens with that's why they call it a two-sided test. Okay, and so there you go. Okay. The last thing, it says this, create a 95% confidence interval and comment on how the p-value relates to the interval and its confidence level. So going back to the last chapter, let's pretend we made a confidence interval with this data, okay? We just made a confidence interval with that right there. So let's do that. You remember making a confidence interval in the last chapter. So we would go stat, we would go test and go down to option A, right? Option A. And so notice it went ahead and entered this stuff for me because my calculator knew I was going to do this very thing. And so our confidence level is 95%, okay, because it told us 95% up here, see? All right, and so let's make the interval. All right, so there's the interval. So our 95% confidence interval is in fact 0.60421 to 0.70829. Those are the plausible values for P. Okay, now those are, and so anything outside of this are not plausible values for P. They're possible, but they're not plausible. Remember, our null hypothesis is that P is equal to 0.6, and our alternative is that P is not equal to 0.6. So when you think, so if you were just thinking about this interval, not really so much the p-value. So here's our p-value. P-value is that. All right, what does this interval tell us about the null hypothesis value? Well, this null hypothesis value is not in the interval. And so it's not a plausible value and it should be rejected. That's what, in essence, that is saying. And that's what the p-value, the low p-value told us to do. So that's the connection between the p-value, the interval, and the hypothesized value. If the hypothesized value is outside the interval, it should be rejected at that level. And we would expect a low p-value, below 0.05. And so this is what we would say. So we would say, and we kind of said something similar to this last chapter. We would say this interval does not contain the p-naught of 0.6. So it should be rejected at confidence level of 95%. Okay? The low p-value, less than 0.05, also tells us to reject p sub naught is equal to 0.6. And so that's the connection there. And in the next video, I'm going to explain this. Well, first of all, this has to be a two-sided test in order for this to work in this way. Okay. But a 95% confidence level is related to an alpha value 0.05. If this had been 99% confidence, all right, our alpha level would be 0.01, 1%. So the confidence level and the significance level have to add up to 100%. We'll explain that more in the next video. But that's it. Thanks for watching this video. That's really the heart of chapter. That's really the heart of chapter 9. If you got any questions about that, please let me know. And I hope you have a great day.